Welcome to the third part of this video series on contactless wireless sensing. In our previous video we discussed about why contactless wireless sensing is required. In this video we will talk about how contactless wireless sensing is done and deployed. Contactless wireless sensing can be classified into four main categories, which include frequency modulated continuous wave based system, a channel state information based system, a wireless sensor networks based system, and camera based system. In the frequency modulated continuous wave system, we look at the commonly used frequency modulated continuous wave radar system, which is a radar system for sensing, localizing, and tracking an object by measuring the range, velocity, and angle of arrival of the reflected wave. And in healthcare, we have a special synthesized signal send system. Then the system analyzes the reflected signal based on its frequency and amplitude to extract information of the observed person. So some major questions to be asked and answered in this particular design include: how do you configure the radar to estimate the range of an object in front of it? What if there are multiple objects in front of the radar system? What is the minimum distance between two objects that can be observed by this particular radar system? Then what determines the farthest distance a radar system can observe? Now we discuss some important features of the Fmcw, and we start with the chip. The chip is essentially a sinusoid wave whose frequency increases with time. As it can be observed from this figure, the chip starts as a sine wave with a frequency of, say, Fc, and gradually increases its frequency until it reaches the frequency of about Fc plus B, where B is the bandwidth of the chip. Hence the frequency is modulated, and this is mostly what is meant by frequency modulated continuous wave. To look at the characteristics of the chip, the frequency versus time plot is a convenient way to represent a chip, and since the frequency of the chip increases linearly with time, it takes the form of S equals to A times T, where S is the instantaneous frequency of the chip and A is a constant. In other words, a straight line with a given slope. And from the figure we can observe the following characteristics of a chip: that a start frequency Fc can be observed from the graph, a bandwidth B, and the duration Tc. Also, the slope S of the chip defines the rate at which the chip ramps up. Now, to look at the Fmcw radar and operations, we know that we can observe that we can now move on to explain how the Fmcw radar, and for this we consider the simple FMC radar shown here, where we can see that we have a single TX antenna, which is the receive and the transmit antenna, and we can also see that we have a single RX antenna, which is the receive antenna, as well as a mixer. A mixer is basically a 3-port device with 2 inputs and 1 output, where for two sinusoid signals, X1 and X2, there is an output signal X out, where its frequency equals the difference of the two incoming signals frequency, and the amplitude also equals the difference of the amplitude of the two incoming signals. The operation steps for this particular radar system, FMCW radar system, are synthesizer basically generates a chip. Then a chip is transmitted by the transmit antenna TX. Then the chip reflected off an object. The chip is essentially reflected off the object being observed. Then the reflected chip is received at the receiving antenna RX. Then RX and TX signals are then mixed in the mixer, and this is the results. The final results is called the IF signal. So now let's look at in details the IF signal. As it can be observed from this figure, the TX chip and the RX chip signals, which are essentially the transmitted and the received signals from the object respectively, we can observe that the signal from RX, which is the receiver, is a delayed version of the signal from TX, which is the transmitter, and the IF signal is essentially a straight line with a constant value f. So now we look at the Fourier transform, which is a central part used in the FMCW radar system. Basically, Fourier transform converts signals from time frequency to from time domain to frequency domain. A sinusoid in time domain, it produces a peak in the frequency domain, as it can be observed here. If the observation window is too small, then a single peak in frequency domain is observed. This leads to loss of information. On the other hand, if the observation window is sufficient, then we will be able to observe two peaks. Hence, we can say that a more extended period of observation deduces better resolution and prevents loss of data. So now we look at multiple objects in front of the radar, where applying the same principle, multiple objects in front of the radar yield multiple reflected chip at RX antenna, which is a receive antenna, as shown in this particular figure. A frequency spectrum of IF signal will reveal multiple tones, where the frequency of each being proportional to the range of each object from the radar system, as can be observed here. To explain now the range resolution of the radar, it is essentially the ability to resolve two closely spaced objects, where increasing the length of the IF signal resolves the objects and differentiates between two closely spaced objects. It also proportionally increases the bandwidth. Hence, we can conclude that the greater the bandwidth, the better the resolution. So we now look at how we can digitize the IF signal, and the resultant IF signal is passed through a low-pass filter to be digitized by an analog to digital converter, then sent to a suitable processor such as a DSP that begins by doing a Fourier transform to estimate the range, the velocity, and the angle of arrival of the object. To recap, we discussed about we discussed that the synthesizer generates the chip, and the generated chip is transmitted. The RX, or the receiver, receives the delayed version of the chip. The IF signal consists of multiple tones, the frequency F of each of the tone being proportional to the distance d of the corresponding object. The IF signal is digitized, where the analog to digital converter must support an IF bandwidth. A fast Fourier transform is performed on the analog to digital converter data, and the location of the peaks in the frequency domain directly corresponds to the range of the object. Now we look at the channel state information based contactless wireless sensors, where they are essentially advanced signal processing algorithms used to precisely extract the channel state information of the Wi-Fi signals, such as the phase shifts, frequency variation, and signal levels. The wireless sensor network-based contactless wireless sensors are basically a set of sensor nodes randomly positioned and which cooperate with each other to monitor, process, and send collected patient's data and their environment to the relevant person. Finally, camera-based contactless wireless sensors are essentially cameras which are used to capture the image of a subject, such as the face, and uses intelligent algorithms to decipher the information, such as confusion, fear, and pain. In the next part, we will talk about the literature review of the contactless wireless sensing, where we will discuss some applications and some already deployed works on contactless wireless sensors. See you then.